Hi everybody and welcome. Today we're going to be talking about horizontal and slant asymptotes. So basically what this does is it improves on the model that we were working on earlier this week where we could just have totally flat or totally vertical asymptotes, and it introduces an aspect that honestly gets us a little bit closer to reality in terms of more complex functions that we're going to see a little bit more frequently in the real world. So a couple of things to note here, and we can look at some examples of asymptotes in our graphs below. But first, let's write down a quick definition. So for horizontal and oblique asymptotes, this is when we have a horizontal or slanted line that a rational function will approach as x goes to positive or negative infinity. So all this is saying is just as the function goes all the way to the right, or it goes all the way to the left, we are going to see it get closer and closer and closer, but never actually touch this line. So in our case here, in the first graph, we can draw one right on this line here. So this is our asymptote because as these blue lines continue, they could go for the rest of their days and they will never truly actually get to that nice horizontal line that we have here. And we're specifically talking about horizontal today. So I know, yes, it is true, we do have a vertical asymptote here as well, but we're really just looking at the horizontal ones. Now, the trouble with this function here is that that's not really the case for this. I mean, we could draw a nice horizontal line here, and it would be true that the function wouldn't touch it, but the function is really not getting close to it. So the important part of our definition here is that the rational function will approach the line. Well, in this case, it actually looks like it's getting further away. And as time goes, that gap just gets bigger and bigger and bigger. There's a bigger distance in between these two. So this horizontal line is no longer an asymptote because the function no longer approaches it. So as a result, there's actually a pretty simple fix. We just have to tilt it. And what happens when we tilt it is the function now approaches it and it still never touches it. So now we have a nice horizontally slanted asymptote, or we call this a nice oblique asymptote. We sometimes call it a slant asymptote as well. So either of those two words, slant or oblique, apply to our second example here. So here is a horizontal example, and then here is our oblique example. Now, the nice thing about this is an oblique or a slanted line is something that we're really familiar with. In fact, we've been doing it for a really long time. It's just y equals mx plus b. So remember that your your b is your y-intercept. So that is just where do we cross the graph. So in this case, it looks like it's somewhere in the range of 1. And we'll be able to calculate that a little bit more clearly. And then for your slope, this is going to be your rise over your run. And if you need to calculate that, just take a quick refresher on the formula, y2 minus y1 over x2 minus x1 when you have two ordered pairs from the line. So some review there from way back when in terms of actually getting the equation of your line. But the nice thing is we won't really be doing this too much from graphs. We'll be able to use fun methods like synthetic division, and that's going to be able to determine our oblique or our slant asymptotes for us. So in order to find these, we have a couple of rules. So rule number 1, if the degree of our denominator is greater or bigger, and I'll write the word bigger up here, than the degree of the numerator. So denominator is the bottom, and then numerator, that's the top. So we're saying the bottom's bigger than the top. So if the bottom is bigger than the top, then we have a horizontal asymptote at y equals 0. So this is an example we actually covered in the last set of notes. So we know this already. We're feeling good about this. We know the horizontal asymptote just occurs on the x-axis where y equals 0. So right there, that line is going to be I don't even know how I made that weird shape. But basically the idea is that this right here, that's going to be where the function approaches. So if it's going up like this, it's going to get really close, but it won't actually touch it. So that's the idea for that one. So an example of this would be if we had something like x minus 3 over x squared minus 8. The degree of the top is 1. The degree of the bottom is 2. The bottom is bigger. Therefore, we are looking at our asymptote right there. Rule number 2. And again, this rule is a second review from earlier this week. So if we have the degree of the numerator, so the top, this time if it's equal to the degree of the denominator, the bottom. So basically what this turns into is the equation y equals the leading term from the top divided by the leading term from the bottom. So this is taking the number in front of our largest degree term, putting it on the top, taking the number in front of our largest degree term, and putting it on the bottom. So an example of this, if we have x squared minus 6x minus 9 over 2x squared minus, pulling a crazy number, pi, just some random number here. So we're just looking at our largest term, x squared, that's the most number of degrees. There is a little 1 that's hiding right there. So if it's ever not written in, assume it's a 1. So our horizontal asymptote in this case is y equals 1 over 2. So all that this does is it just takes that x-axis asymptote and it shifts it up by whatever that number is, or down if it's negative. So in this case, horizontal asymptote comes at 1/2 or 0.5. So the function now will get close to that line, but it won't ever actually touch it. All right, so let's move on to our third rule. And I'm going to make just a touch of space here. So rule number 3. This is the only case we haven't discussed yet, which is when the degree of the numerator, so the top, is greater than the degree of the denominator, the bottom. So earlier this week, I told you that if this is the case, you do not have a horizontal asymptote. And I didn't lie to you. It's true. There is no flat line. What happens in this case, though, you can probably guess, this is where the oblique or the slant comes in. So that flat line doesn't move up or down. In this case, it actually tilts, and we get a slant introduced. So we end up with an oblique asymptote with an equation of y equals mx plus b. And the way that we find this is synthetic division. So let's say, for example, and we'll do another crazy one so we're prepared for all of the tricks up my sleeve here. So x squared minus 7x minus pi again, so some just crazy number at the end, and we divide it by x minus 3. So we'll go through our synthetic division steps in order to solve this. So we'll first take x minus 3, set it equal to 0, and get x equals 3. We'll take the numbers, so 1, minus 7, and minus pi. And then we'll actually do our operations of synthetic here. So 1, minus 4, and then minus 12. And here is a fun new thing. Our remainder, that final term, no longer matters. So just for this only, whatever that number for our remainder is, we don't care about it. We are just going to take our 0 and further terms. So whatever this term is, ignore it. If it's a crazy number, doesn't matter. If we have pi and some random variables introduced, things like that, does not matter. We are just looking at from 0 degrees forward. So -4 and x are introduced here, and we end up with an oblique asymptote y equals 1x minus 4. So we go down 1, 2, 3, 4. Then we go up and over by 1, up and over by 1 because that's our slope. And this nice slanted line of 1x minus 4 is our asymptote. So a function might do something crazy like this. And it might also come down from here and do the same thing. And that would be our asymptote highlighted in red here. There's that 1x minus 4 line. So that's the idea with synthetic division, and that's what's going to help us out to solve. And again, we don't use our remainder. We're just using our x term and our constant term when we're solving for our oblique asymptotes specifically. So taking a look on the back here, a couple examples to help us practice. So a good first step, we're going to want to determine the degrees for the top and the bottom. So degree for the top here, x squared is 2. Degree for the bottom, x squared, also 2. So we have the case where top equals bottom. So let's take a look. So that would be rule number 2, top equals bottom. So leading term divided by leading term. Okay, so leading term on the top is -1, and then leading term on the bottom is just 1. So in this case, we have a horizontal asymptote at just y equals -1. So on our graph, it would be just below the x-axis where y equals -1, and that would be our horizontal asymptote in that case. For the second one, we'll keep going. So the degree for the top here, x to the third power gets us 3. Degree for the bottom here, x to the second power is the biggest term, that gets us 2. And remember here for degrees, we only look at the biggest term. We're not looking at all of the terms, just the biggest one. So top bigger than bottom, top bigger than bottom. It says oblique asymptote, use synthetic division. Okay, so I'm using rule number 3, oblique asymptote, using some synthetic division here. So we'll go back down to this, and we are going to be looking at doing some synthetic division, or in this case, long division as well as the second option. So the challenge with this one is on the bottom, synthetic division doesn't work because we are not going to have the opportunity to use it by setting the bottom equal to 0 and having one number off to the side. So unfortunately, sadness, we are going to be doing it the old-fashioned way. With long division. So for long division, a quick refresher on some of those old skills. We want our first term to match up with our first term here. So 1x squared times what gets us 16x to the third. So that would end up being 16, and then x. So by working through and doing that, we are going to be able to get ourselves a nice distributed term here. So 16x goes to all three of these things. And one thing that we want to make sure we're doing is lining up our like terms when we do this as well. So 16x to the third, and then we will get 32x squared, and then we'll end up with just 16x here. So once we get to this, we are going to subtract each of these terms from what we have. So subtracting here means distributing in that negative to all of these, and we'll end up with minus 16, minus 32, minus 16. So our first term, 16x to the third minus 16x to the third, that cancels. That minus 32x squared comes directly down, and then minus 16 and positive 2 leaves us with minus 14x. And then we can bring down our positive 8. So our next step here is we have to multiply our first term so that it matches our first term again. So first term matching first term. So in this case, we would need, the x is already matched, we just need 1 to match 32. So 1 times negative 32 gets us negative 32. So we will distribute this now once more. So minus 32, minus 32, minus 32. So now once more, we can subtract everything that we have. So we'll distribute in the negative to all of our terms. So our first term cancels. We get 50x here. And then we're left with a 40 there. So the nice thing is that in this case, x squared does not go into 50x because the x term is bigger. We don't have to worry about our remainders, just like before synthetic division. So typically we would put this 50x plus 40 over our x squared plus 2x plus 1, and that would be our remainder. But again, not focusing on these remainders for today. We are just looking at our answer. So this one would have an oblique asymptote at y equals 16x minus 32. So a bit of a challenging question there because of the degree of the terms and not being able to use synthetic. We'll take some time dedicated in person to make sure that we're all feeling okay with long division because it is a bit tricky when the terms get a little bit bigger, but something that we've done in the past, but definitely something that we can take some time in class to review as well. So final answer for this one, we have an oblique asymptote at y equals 16x minus 32. So thanks for watching the video. As always,